guess first I'll start with a disclaimer that we have the opportunity to select Connor Bedard. I can't necessarily disclose anything of that nature, anything further. But yeah, thanks for the introduction. I want to start by thanking the organizers. I think conferences like this are key to maturing the hockey analytics field, especially a venue where researchers can come and publish their work and share their work and get very valuable feedback through the peer review process. It's been great, and it's really it's aligned with a lot of the computer science conferences that we were used to attending, used to submitting to and publishing papers in. So this has been great. It's been a great conference so far, and I look forward to the rest of it. So I'm here presenting our new paper this year called Analyzing Passing Metrics in Ice Hockey Using Puck and Player Tracking Data. And this is work done with a number of collaborators, but I added the pictures of myself, my brother Dan, and Tim because we are here and present. So I am as mentioned, I am a former Division I ice hockey player. I was fortunate enough to play in graduate school too at the University of Waterloo. My brother Dan is a former Division I ice hockey player and is currently rumored as the Connor McDavid of the lower European leagues. And Tim is plays in Waterloo and is now my teammate. I've graduated to play with Tim on Tuesdays and Wednesdays. So yeah, diving into it, I kind of want to start this talk by highlighting this work by Ellis in the early 80s, which essentially comes up with a classification system for different sports. And the one I want to touch on is called invasion games. And so ice hockey falls in this category of invasion games, where they're defined as teams intermingle and attempt to outscore the opponent by invading the opponent's territory. So games with similar characteristics or football or basketball. And unlike striking games, which you could think of as baseball or cricket, invasion games, as we all know, are a lot harder to analyze and harder to understand how to construct teams and how to win games. And so for 100 years and even today with the evolution of expected goals and such, metrics disproportionately capture offense, right? We have goals, assists, points. Expected goals rely on shots on net, but successful teams to actually go and win games and win championships, you can't necessarily have 20 players that fill the net. You need players with diverse roles and diverse abilities to work together with those players that can generate offense and score those goals. So kind of the key thread behind a lot of the work that we focus on at Waterloo is, can we capture more characteristics about how players behave? And so with the adoption of puck and player tracking data in the NHL that we're fortunate to have access to through a partnership with the NHL, we aim to kind of answer this question. What can we tease out of the tracking data to help us understand what players can do and what they're good at? And so I'm going to highlight some related work because this ties a lot into my actual PhD work, is that role diversity and specialization is important for team performance. This is a known fact across organizational psychology and in a lot of my work in multi-agent systems and multi-agent reinforcement learning. And this has also been studied in football with passing metrics. So diversity in how players pass and where they pass leads to successful teams. And just the last point of related work here, which I'll get into in more detail, is the last papers that our group at Waterloo has published, where we basically try and model passing behaviors and pass availability and stuff like that. So we're trying to adapt this into hockey using the tracking data. So before I dive into the really related work about the models. I'll actually pause by saying the first part of this talk, like I'm going to give a high level overview of the passing models because that's going to help inform the contributions of this paper in the second half of the talk. So first, the puck and player tracking data it's a hardware-based system in the NHL where players wear these sensors on their right shoulders, and the puck has a chip type thing in it. But essentially, we get the X, Y, and Z coordinates for all the players and the puck multiple times per second. And this data is annotated with event data. So we have say a pass or a shot, and we know the entire state space, or we know the entire maybe not like the whole state space, but we know the X, Y, and Z coordinates of all the players on the ice. So they appear as points on a three-dimensional plane. But for this work, we're just going to use the X and Y coordinates, so a two-dimensional plane. And so I'm going to just dive into these two models that we use to basically analyze the distribution of players in the NHL. That's what this paper is we take these models, and in previous work, we implemented these models and we proved them out using a smaller data set, but now we have an entire data set an entire season of tracking data. So now we dive in and we want to analyze the distribution of players. So first, I'm going to dive into the passing lane model. So the passing lane model essentially tries to characterize the available space between a passer and a receiver. And so the way this works is, imagine we have a passer P and a receiver R. And in this scenario, we have two opponents. So how can we characterize how open this pass is, or the available space? The algorithm is more complex, but that's not what this talk is about. So a way to visualize how we do this is essentially we have this parameter gamma that helps characterize the size and shape of this passing lane. And you might just think of this as growing. As we increase gamma, we grow this shape until it contacts the nearest opponent. So these are the parameters of the passing lane model, and the shaded region is what we call the passing lane, and there's several characteristics that are satisfied with this model. And so essentially this pass would have an availability, a gamma value of 0.55. And so we can aggregate this across all passes and a bunch of different scenarios, and this kind of gives us an idea of how open this pass was, or how small the passing lane was for a completed pass. So in last year's LINHAC, for those of you that were here, we extended this passing lane model to indirect passes off the boards. So in this case, what we do, and these are off straight boards. So what we do is we essentially mirror the ice in 4 different directions, and then we can just model the pass as a direct pass. So here we mirror it over the boards, and we can just use the direct passing lane model, and then we fit it to the reflected opponents and the real opponents on the ice. We also incorporate the expected movement of players. So this takes in, obviously, like hockey's very dynamic. If I pass to where a player is, by the time the puck gets there, the player is going to be 20 feet away. So the model that we use in this paper also incorporates where the players are going, and we project players into the future. So in this case, we project the receiver and the opponent into the future, and then we essentially fit the passing lane model to where the players are expected to be based on their speed and the expected speed of the pass. So we were at the pub last night, and I decided that I am going to recycle some drone footage from last year. So I don't know how this is going to show up, but here you essentially see I make a bank pass off the boards, and we can capture passes like that. And then here's a stretch pass that takes into account the expected movement of the players. And then here's just an in-game scenario. We just recreate this where, up and over and then back, and just kind of mess around from here. And here's a real game scenario. I don't know how this is going to show up, but I'll play this a few times. Essentially, what we do here is on the face-off, when we want to show the best passes, or the most available lanes for 47 to pass the puck. So here the face-offs won and 47 has it. It's kind of fast, but we have these numbers above the players that characterize how open those lanes are. And in some cases, it may be the indirect pass. And if you follow 91 here, 91 immediately stretches up the ice, and we see that the most available pass to 91 is off the boards, measured by the model. And this is in fact what 47 ends up doing, and it leads to a goal. So I'll just let it run out one more time. Okay, so that's the passing lane model. We're going to use that model to analyze the distribution of players in the league. Now to the pass overtaking model. So one of the interesting things about invasion games, as opposed to things like striking games, is you need to advance the puck. You need to get the puck into the opponent's territory, and to do that, you need to advance the puck beyond opposing players. So this model we proposed in a 2021 paper, and this is heavily inspired by work in football, where, again, say we have a passer P and a receiver R. If P wants to make this pass, the defensive status of this opponent is changed, right? First, they were on the defensive side of the puck. Once the pass is made, they're on the offensive side of the puck. And so now say we have a second opponent here. When this pass is made, the defensive status of this opponent is not changed. They were on the offensive side of the puck, and then after the pass, they're still on the offensive side of the puck. And the same goes for if the opponent were standing here. They're still on the defensive side of the puck, so they're not considered overtaken with the pass. So the distance that we're measuring here is to the opposing net. So it's not just up ice, it's all kind of measured to the opposing net. And so in a whole, the way that the model works is, say now we have 5 opponents, and there's 3 possible opponents that the passer can overtake. There's 3 opponents between the passer and the net, and say they make this pass, it overtakes 2 of them. And so what we end up doing is we treat this as a zero-sum game. So the passer gets a plus 2/3, and both opponents that are overtaken get docked 1/3. And the reason why we implemented it like this is so that defensemen didn't accumulate more and more and really separate themselves. But we'll dive into the results of this in a bit. One of the contributions of this paper is that we needed to clean the data a little bit. And so we have event data that augments the tracking data, but sometimes the timestamps are a little late on the pass, but we need these timestamps to be precise so that when we model the passing lane, it gives a full accurate picture of where everybody is on the ice and how big that lane is. You might imagine if this puck is already close to the receiver, then the passing lane might look huge, but in reality, the pass didn't have that big of a lane. So essentially, the goal here is to find a new timestamp T prime for the pass, where we can back up time. We can basically rewind the game until the puck is within 4 feet of the passer. And then we use this new time T prime as the time to then implement the passing lane model and the overtake model and stuff like that. And we chose 4 feet based on internal conversations and measurements and conversations with people at the NHL. And so this ended up cleaning almost all of our data, but there was still 2.6% of passes that the puck just never got within 4 feet of the passer. So we omit those from our data set. So now diving into the main overall contributions of this paper, we analyzed 4 different passing metrics across the entire league. The first, so they're all averaged per game. So that's why all of them start with AVG. So average per game. The first is OVT 20. So this is this is the fraction of opponents that a player overtakes throughout a game. So that one player got a plus 2/3, and we're just going to treat this like assists, say, or goals. Like you're just going to accumulate these throughout a game. So and we scale it to 20 minutes. So this _20, because it's a total, we're going to scale it to as if this player played 20 minutes to kind of bring everybody on a level playing field. So we can actually fairly analyze players across the league. The next one is BTT20, average BTT20. This is on the other side of the coin when those players were beaten by passes. So high numbers of BTT20 are probably not very good because you're like a hard forechecking winger who ends up getting beaten with the first breakout pass. But essentially, this is like the fraction that a player gets allocated to the player that gets beaten by a pass. So these two metrics together, what we actually propose in a previous paper is if we take a difference of these, or we basically do OVT plus negative BTT, we get a passing plus minus. So it works the same as plus minus, but essentially one of the limitations with passing plus minus, which we're going to dive into later, is that players that overtake a lot but are also overtaken a lot could end up looking the same in passing plus minus as players that don't do anything. So we're going to kind of dive into that in a few slides in one of our results. The third one here is average OVA. So this says this is the average fraction that a player overtakes with each pass. So it says I'm the passer, I have the puck. What's the expected overtake value for whatever pass you're going to make? And then we have average PAA. And so what this is the average gamma value of your passes. So the average passing lane size for the passes that you complete. The data set that we're going to analyze is over 1,200 NHL games. There of the 2021-2022 season, there were actually 1,312 games, but some of them had some data irregularities that we couldn't actually process those games. So we ended up with just over 1,200. We also filter players so that we take out players that played less than 10 games and had averaged less than 10 minutes on ice so that they didn't get disproportionately skewed. And so our final data set has 750 players in it, 478 forwards, 272 defensemen. So now diving into the results, we're going to first show some CDF plots, which essentially show on the x-axis, I'll dive into these individually, but just as a high level, on the x-axis, we have the value of each metric. And on the y-axis, we have the fraction of players for each position that have at least that value. So here, say, we find that forwards tend to complete passes with slightly smaller passing lanes. So here we have average PAA. So values to the left would mean smaller values of PAA, which means smaller passing lanes. And we find that forwards complete slightly smaller or passes with slightly smaller passing lanes. But every time a forward is about to make a pass, we find that the average OVA, so the expected overtake value for forwards, the variance is much larger. It's 2 times that of defensemen. But when we actually accumulate OVT over a game, so the fractions that players overtake throughout a game, we find that defensemen blow forwards out of the water in terms of overtaking players. And what's interesting is because the forward curve is more vertical and the defenseman curve kind of has more of a slant to it, what we find is that the defensemen higher on the spectrum tend to overtake players at a higher click compared to their peers than the forwards do, right? Like the top forwards on this curve have kind of a more similar overtake total compared to the other forwards than the defensemen. The top defensemen in this tend to really separate themselves. And so here we just kind of take an extra look at the average passes made per 20 minutes and average passes received per 20 minutes for each position, because we're looking at the data and we kind of noticed something interesting, and that's that defensemen typically complete 5 more passes than forwards. So this is the same across the entire distribution. There's pretty much a 5-pass gap between the distributions. But even though like defensemen receive slightly more passes than forwards, but the gap is a lot smaller than 5 passes. And so what we end up finding is that we go into this in the paper a bit, but intuitively, if a forward has the puck at 5-on-5, full even strength, when a forward has the puck, they can pass to 2 other forwards or 2 defensemen. But when a defenseman has the puck, they can pass to 3 forwards and only 1 other defenseman. So what we can conclude here is that defensemen pass to forwards 3 times more than their other defensive partner. And so this helps describe why defensemen accumulate a lot more OVT, because throughout a game they're passing to forwards 3 times more than their D partner. So if they go D to D, they're not going to get OVT, but if they end up passing up to their forwards, they can actually have the opportunity to overtake more players. So just an interesting insight there. Looking into this passing plus minus metric that I mentioned earlier, one of the limitations is that players that are really active in overtaking and players that do nothing in terms of overtaking could both be 0. But if we actually cross-reference these, we get more of a picture as to the distributions of these players at different positions. So along the x-axis, we have average OVT 20. This is the total of overtaking opponents with your passes. And then average BTT 20. This is being beaten by opponents. And so the main thing we're looking for here is to see, is there variation in these players? Are there different types of forwards? Are there different types of defensemen according to these metrics? Because then these might be useful in constructing lines or constructing teams. You want players that have different characteristics. And so amongst a player's games, we can compute 95% confidence intervals to determine if these variations are just noise or if they're actual performance from these players. And these are just rough approximations like the visuals are, but we actually in the paper have calculated confidence intervals. And what we find is that for average OVT, if we take the lowest player at each position, the median player at each position, and the highest player at each position, these intervals don't overlap. So it's pretty significant that these players are actually performing and separating themselves from each other instead of this just being random noise. If we look at BTT, there's no intersection in confidence intervals for BTT. So what we find is that along both dimensions, there's different types of forwards. So this isn't just one type of forwards with random noise. This is actually these different types of forwards regarding overtaking or being overtaken. So and it's a pretty circular distribution. So what we can conclude is that there's forwards that overtake a lot and are also overtaken a lot. There's forwards that don't do anything, and there's forwards that overtake and don't get beaten, or vice versa. On the defenseman side, we see that 2 of the confidence intervals do intersect, and so we can't necessarily say that there's a large distribution, and we do find this in the defensive cluster. So again, this kind of says that defensemen mostly vary in how they overtake opponents. There's not huge variation in how defensemen are beat, but again, this is aggregated throughout an entire season. So we can then take these metrics and compare with traditional statistics. So here we compare with assists 82. This is assists scaled to 20 minutes per game, and scaled to if a player played 82 games. And so the point of this plot here on the left, we have assists 82 on the x-axis and average OVT 20 on the y-axis. This is overtaking players, the total of overtaking players with passes. What we find is that there are players that do overtake opponents a lot that don't necessarily have high numbers of assists. And so these players wouldn't necessarily show up on the game sheet in terms of assists, but they're making significant passes for an invasion game like hockey. They're advancing the puck beyond the opponent. On the right here, we have assist 82 on the x-axis, and we have average PAA, which is the passing lane values. So again, higher values on the y-axis mean that the passing lanes are huge or bigger, and the player's just making easy passes. Lower values here mean that the passing lanes are smaller, and you kind of need to thread the needle more often because these are aggregated values. And interestingly, what we find is that there's no players that have both high assists and large passing lanes. So what's kind of interesting is that the players that do get lots and lots of assists tend to all have smaller or more restricted passing lanes. So maybe this is indicative of passing ability. Lastly, this is the last thing I'm gonna really touch on here is we only have one season, but we can kind of do a stability analysis here of these metrics where we take the first half of games and the second half of games and we just cross-reference them. And so if they matched up perfectly, if the player was completely consistent from the first half to the second half, they'd just be in a diagonal line across here. And so what we find is that average OVA, this is the expected overtakes given a pass. This has a correlation coefficient of 0.87. Average OVT, this is the total of accumulating throughout a game, has a correlation coefficient of 0.99. And average PAA, this is the average passing lane size, has a correlation coefficient of 0.89. So what do these mean? This is pretty significant considering that when you compare this to points and goals, all three of these metrics are more stable and kind of have higher correlations than points and goals when we compare the first half to the second half. And like any work, ours is no exception that there are several limitations, but this really opens a lot of directions for future work. First, these are all aggregated across seasons and we have no spatial component to it. So essentially you could tease this out by manpower to gain more insight into power play passing or stuff like that. Goal differentials, zones, and potentially coaching strategies, like maybe coaches press really hard on the forecheck and that's why a player gets beat a lot. But this also kind of offers the possibility to analyze how this changes team to team. And so we listened to the analysts yesterday talk about pre-scouts and everything like that. Like perhaps this could be helpful there. We acknowledge that some of the players in our data set, we filtered for time on ice and games played, but there were some players that played 10 minutes a night, but had one pass or maybe 0 passes. So maybe future work could actually filter out those players. And our data set only has completed passes, but there's several companies here that do track incomplete passes. So perhaps having that data could be useful in analyzing patterns between passing lane availability and things like probability of completed pass, stuff like that. And so finally, in summary, just some discussion points. We find that forwards are diverse in the passing plus minus metric. There's a big variety in how forwards play. And so this is probably very helpful in team construction or roster construction or things like putting lines together. Defensemen overtake significantly more than forwards. And the highest defensemen for overtake total tend to distinguish themselves from their peers more than forwards. And what's interesting is that defensemen pass to forwards 3 times more than their defensive partner. Our metrics have more stability than points and goals. And finally, these can be more important, or these can be very important for things like team construction and typical team forming algorithms that you would find in the AI literature. Maybe not like the buzzy AI that's been going around now, but more in the multi-agent systems literature. There's a lot of work on coalition formation and team forming, and to do this, you maybe don't just want to measure things like expected goals or offensively based metrics. And finally, big thanks to people at the NHL, AWS, Rogers, and various funding sources for helping us out through this project. And you can scan here for the paper or just find it on the LINHAC proceedings. So thanks. Let me know if there are any questions.
Questions from the audience? I'll ask a question. So I mean, here you mostly showed distribution statistics, but I assume that you peeked into some of these stats that you showed up. Was there any player that were sort of, okay, this is really surprising that this player have these statistics?
Yeah, I'd say we had some fun kind of diving into some of it. Sometimes we would think the nice thing about the CDFs is when they have long tails at the top, you kind of think, okay, there might be an outlier, so maybe it's a bug or something. And there were some where this one player, for instance, had really high average PAA. The gamma values were really big, and so we were like, this was earlier on in the project when we were only doing a subset of the data set. And we were like, oh, okay, like what's going on here? And we actually looked at that player's passes, and they made a insane amount of just everyone's going to change, and they would just kind of like pass to their D partner with nobody around. And and so it was one of those things where we were like, oh, okay, there must be a bug. And then we actually went and looked at that player's passes, and it was like, I think 30% of their passes were just like, oh, there's no one near me, I'm just gonna like dish it over to my partner just for fun. So,
but in terms of like just follow up in terms of like the names who were very good at some of these statistics, like I'm not a huge follower of hockey, but I do follow some hockey. I didn't recognize most of the names, so it felt like, yeah, we might be onto something, because there may be value to some of these players that you aren't seeing from the game sheet.
Mm-hmm. Okay. Yeah, no, nice. And I mean, another thing is that you only consider completed passes. So I mean, this person might otherwise just dump out the puck or something like that.
Yeah. So again, like we really, like, one of the things we talked about in the last papers too is when we have incomplete passes, like actually identifying or trying to figure out what the player's trying to do is difficult.
Yeah.
And so that's its own research problem on its own. But if we had some notion of incomplete passes, then it would be very interesting to kind of use some of the models here to derive some probability metrics.
Okay.
Like that, so.
Yeah, and then another quick question. So I mean, here you looked at average values for the players, and I mean, to some extent, you could imagine that, okay, some players have an average, but they're sort of high risk, high reward players.
Yeah.
So the average looks one way, but the distribution would look completely different. So did you try to look at standard deviations for individual players, and if that sort of were a useful metric?
Yeah, for sure. So we kind of got into that a bit with the confidence intervals, but yeah, we kind of struggled about how to visualize things like that. So the confidence intervals give some notion of variation, but yeah, you're right. It's the same thing with goalies. Like, do you want a goalie that gives up 0 goals one game but 6 goals the next game, or just gives up 3 consistently? So yeah, that's another way. Like we just analyze averages and the distribution throughout the season, but you could look at, okay, which players have the highest variation? Do we want a player that could get beaten by like 15 passes a game? Like, maybe not. But
or the person is reliable, I know what I get, versus sometimes he's crap and sometimes he's brilliant.
Yeah, exactly. So like those, I highlight here at the end, I highlight team construction and team forming algorithms. And so those are all things that could be used in kind of those settings, and figuring out what kind of lines you want, which players should play together.
Yeah. And for that you want many different metrics, and this would be some interesting, useful ones. Yeah. No, thanks. Let's thank David. Yeah, please go ahead.
Sorry, I wasn't quick enough. So 2 questions. So maybe I missed it and you said it, but what are you like explaining? What's your Y variable, so to speak? And my second question would be, just from what we do you have any idea how much better the model performs if you have the information of the positions of the defensive players as compared to just the passing information, just the puck information? Do you know what I mean? With that second part,
can you elaborate a little bit? The first one, I missed the what variable in the first question.
So basically, what are you explaining that you're passing? Like, is it advancing the puck toward the opposition net?
Yeah, like the overtaking model, yeah? Is that what?
Well, both really. So with the, just help me understand with the passing lane, is it like the bigger the passing lane, the better, or like there must be something like the further we get to the opposition net, the better, or something like that?
Yeah, so there's two different models. The passing lane model is the same regardless of where you are on the ice. So it's just a way to, I guess this one works. It's just a way to measure the available ice between two players. So it doesn't necessarily mean if it's better or worse. Like I'm not gonna, if I'm doing a D-to-D pass and everyone's changing, I'm not gonna wait. Well, maybe it's good to wait until a forechecker comes and then make the pass. But like, it's just a descriptive way to say how open is this lane. So essentially what you could do is you could parse it and say, okay, I only want to look at Nikita Kucherov's passes when he's on the power play, on the half wall on the power play.
But sometimes we think about it as the difficulty level, or the risk level.
Right.
And so the
Wide open is easy, and then the smaller is
so bigger numbers are easier and less risky, and smaller numbers are tighter passes and more risky and possibly more difficult.
Sure. So just for context, so like when we analyze the, you know, the defensive potential or the threat, however you want to call it, after every action, be it a carry, be it the pass, whatever. But with the data sets that we have, we don't have we're not tracking the players. So for me, it would be really interesting how much better model result you have when you have those defensive players. Hence my question, like if you, I guess your model only makes sense if you have the positions of the defensive players.
Yeah, like it fits exactly, well, to the positions, but the expected positions of the players. So yeah, we need kind of the other side. And granted, most of what I showed today is from the passer's perspective, or except for like being beaten by passes. But at the same time, you could look at how a defenseman closes passing lanes. Like that's something we talked about in a previous paper, where it's like who's actually closing those passing lanes the most or more often, and how many lanes. Because like you might imagine, I don't have a figure here, but you might imagine like as a passer at even strength, I have 4 other passing lanes. Like I have 4 passing options, the 4 other teammates. And maybe there's one defenseman that's closing 2 of those the most. So you could aggregate it on the defensive side too, based on like this opponent. Or I guess like this is a better description of it. Like opponent 1 is the one responsible for this lane, whereas opponent 2 is not really restricting. They'd have to go closer and really shrink that so that it would maybe be like that if opponent, let's see, if opponent 2 was like here. But yeah, we need the actual locations of the players. And then yeah, with the tracking data, we get their expected locations based on direction of travel and how fast they're moving and stuff like that. So
yeah, no, I mean, great job.
Because we have all that data, we focus on metrics that make use of that data, right?
Sure. Yeah. No, for me, I think like, you know, there's I think 1,400 passes a game, something like that. It's certainly a very important aspect of the game, and if we can combine, you know, your insight with then that business metric or that Y variable of threat or whatever else, I think there's a lot of value in that.
Yeah.
Great job.
Thanks. Anything else?
Yeah, let's